Okay, good morning, everybody. Great to see so many people who attend the workshop. My name is Markus Püschel. I'm from the other Swiss university in Zurich. And I will just put out a few thoughts about the connections between DSL and performance, as Martin mentioned, and also TARC. DSLs are now actually used in this space, meaning with the goal of really improving performance. And I will give just some reasons why that is, and then also very briefly introduce three of the efforts that you will see in the workshop. And in essence, so the picture that goes with this, and I will explain this in a little bit, is this one up here. So first some words about performance, right? So performance matters, of course, and here I just give an example. There are many applications nowadays that for which performance is really crucial. And in particular, this happens in all forms of mathematical computing, right? So you see here lots of applications, and many of them, if you look really into the guts of what's going on, it's mathematics, right? And of course, we have scientific computing, but much bigger domains are, of course, multimedia processing, signal processing, communication and control is like the big thing in the embedded domain. Security, of course, right, more and more important. And then more recently, these two domains have really taken off, right? Machine learning, data analytics, optimization, that's kind of where much of the action is nowadays. So in many of these domains, performance is really, really crucial. And by performance, I mean short runtime, okay? So you want to run things as fast as possible, because then maybe you can run larger data sets, you can do it in real time maybe, you can use better algorithms and so forth, okay? Okay, good. So, of course, in computer science, we have been thinking about fast runtime for a long time, and so the traditional view is sort of shown here. So when we want to achieve performance, we have to go through these steps, and the red one or magenta ones are the ones where typically performance happens. Okay, so let's say you have a given problem. So first, you want to choose a cheap algorithm, right? One that is asymptotically optimal or even precisely optimal. Okay, that's of course the most important part, right? Can rarely beat an n log n algorithm with an n cube algorithm, for example. You choose a cheap algorithm, then you have it. Then you give it to a good developer. You choose a language. Let's say could be C. C++ is very often still the language of choice if you want to really have the best performance, right? Implement a reasonable function. Then, of course, you compile it, choosing a good compiler and all the optimization flags. And then it should run very fast on that given processor, right? So you see performance really happens in these two places, right? Choose the best algorithm and that the compiler handles all these ugly low-level details. And then you have really a very fast program, right? So that's the typical standard workflow. And the question is, how well does this work, okay? So, because this looks like there's really no problem, right? Fast runtime, high performance is really not an issue. And I pick as an example, those of you who know me know I like Fourier transforms, so that's the example I'm going to pick. And those people who have actually taken my class already have seen some of these slides. The Fourier transform is a relatively simple, it's a kernel, right? It's nothing as complicated as a whole heterogeneous machine learning algorithm, but it's really, really important. It's used across disciplines. So you need really fast code. So what I show here is a performance plot. So here on the x-axis is the input. And typically you compute the Fourier transform on 2 power sizes. And so you start from 16, 2 to the 4, up to 2 to the 20. So these are actually the most relevant sizes, right? So for example, just in a wireless transmitter or receiver like 802.11, the sizes that are used are typically in this range here. Okay, so we take this approach, we pick an optimal algorithm, minimal operations count, and we implement it in C. So for example, you can do this by just getting the code out of numerical recipes. Okay, it's a book that has C functions. And you measure the performance that's shown on the y-axis, and this is not runtime, right? It's performance. Floating point operations per second. So think of it as inverse runtime. Okay, the higher the better. And this is some arbitrary scale that I chose to display things well. So we do numerical recipes, is a reasonable C implementation, and it's a short program, and you achieve this performance here. And this is compiled at the time we did this experiments with actually the Intel vendor compiler, all the optimization flags. Okay, so if you do this, you think, okay, that's fine, this is great code. But maybe you really care about performance, so you look around, and then maybe you find other implementations. You benchmark all of them, and it turns out at the time we did this, the fastest code actually achieves this performance. Okay? Has the same operations count, very small differences. It's the same platform, which is a quad-core Intel system, and you see there's quite a difference. Okay? Actually, for small sizes, it's a factor of 12, and for here, the maximum difference, actually 35x. Okay, 35x, so a huge difference. Okay, and you see also something weird happened, right? Because this is the size of the source code somehow increased by a factor of 1,000. Okay, so some weird things happened there. And this is actually a common theme. If you optimize for really hardcore performance, the code size typically goes up. So this at this time was probably the fastest code on the planet.
Where's the information that the code size went up?
I put this here, 1 kilobyte, 1 megabyte source code. That's the source code size.
Oh, I see.
Yes. Okay, so then you say, okay, Fourier transform, yeah, it's complicated, I don't care about it. But we come to this in a second. So the first question to answer is, why is this? Where does this performance difference come from? And here I show you how you get from the bottom line to the top line. So this here is a standard C implementation. If you just work with standard C, you can get actually a 5x by improving the performance, by in essence increasing locality, improving performance for the memory hierarchy, optimal usage of the memory hierarchy, optimal cache usage, and optimal usage of the registers. You can get a factor of 5. That's without using any form of parallelism, okay, just a factor of 5. Then, of course, Intel has vector instructions, SIMD vector instructions. If you use them in a close to optimal way, you can get a factor of 3. That's SSE. You could maybe think of getting a factor of 4 maximally, but you don't get it. Okay, factor of 3. And then it's a quad-core system, right? So obviously you can parallelize. That will only work for large sizes, right? Because otherwise it doesn't pay. And then you can get another factor of 3. It's a quad-core system, but life is not perfect. Okay, so you see that's where the difference comes from. Locality optimizations, memory hierarchy optimizations, vector instructions, a form of parallelism, multiple threads, a form of parallelism. Good. So what we see is somehow we would like the compiler to take this code and produce this performance, but the compiler somehow doesn't. So you have to do it by hand. And what is it that you have to do by hand? Well, this is what people often refer to as this guru or black belt performance programming knowledge. You have to completely restructure the algorithm. So the code that does this is completely different from this code. I mean, if you look at the source code, you wouldn't even see that this does the same thing. Okay, it's not like a little tweak on a loop or something. It's completely different code. Because from here to here, you have to completely restructure the algorithm, change the code style, and so forth. To implement parallelism well, right here you use intrinsics for vector instructions, here you use threading directives, and again, the code changes completely. Okay, the whole algorithm has to be changed. In essence, you have to restructure the algorithm to adapt it to the structure of the microarchitecture if you want to have the best performance. You have to choose proper code style so that the compiler can handle it well, and so forth. It's really a nightmare. It's very difficult to do this. Okay, very few people know how to do this. Yes?
Is the question up here?
Pardon me?
Is the question up here?
Yeah, of course, if I can answer it. Yeah.
You know, what strikes me is, you measure performance in gigaflops per second, right? But you talk about different algorithms. But is it still fair to compare this?
Yeah, because they have the same op count.
They have the same op count?
Yeah.
At random, not just because I was...
After compilation, they have the same op count, plus minus 15%.
But some transformers might actually change the algorithm to the extent that it's not the same op count anymore.
That's true. It's a very good point. Everybody who takes my class knows it's forbidden to put into the same performance plot two algorithms with completely different op counts, and this doesn't happen here. Exactly. So, but the FFT is a very controlled thing. So actually there are bounds and best known algorithms and so forth. So it's a fair, it's 15%. So from the op count difference from here to here is minor, really minor. So it's fair. Okay, so this is very difficult. Now, okay, this was the Fourier transform example.
Wait,
yeah.
Go back.
Yeah,
you haven't commented at all
okay.
on the most interesting fact.
Okay,
which is you have a huge variance in performance depending on the size. Why does that happen?
Oh, why does that happen? Okay, you have a huge variance. So, okay, So here the performance goes up because you start using all 4 cores. Okay, so here it's relatively flat. Here it goes up, you use 4 cores. Here it comes down because roughly at this point in time, the working set of the computation, which you keep reusing, doesn't fit into the last level cache anymore. So that means from here on, you're in a different regime where most of the time you spend more time moving data relatively to performing computations.
Why don't you use 4 cores for smaller jobs?
Pardon me?
Why can't you use all 4 cores for smaller jobs?
You can try it out, but it doesn't pay off. Actually, it's a surprising thing that such a small problem size, which executes really in milliseconds, like here, can already be parallelized efficiently. Because you have an overhead when you parallelize. And for very small sizes, it doesn't pay off. Confirmed by experiments.
So it looks like there's a very narrow range where we can parallelize effectively.
Yeah, you mean from here to here?
Yeah.
Yeah, it's true. I mean, even here you get a speed up.
Parallelizing very ineffectively there, right? You'd be,
Well, the speed up is not so bad, but yeah, this is a problem. Nobody has been able to overcome this, no matter what tricks. It's the Fourier transform has inherent a relatively low operational intensity, meaning data movement to operations. So the reuse is roughly at the order of log n, and that's why this is inherent. Yes?
So if I understand it, that graph is essentially a single operation done sequentially. So essentially you parallelize a single operation, but you don't parallelize multiple operations.
That's right.
So you don't do overall throughput here.
That's right. If you're in sort of a batch mode where you do many FFTs, then it's better to parallelize over the batch, and then you can probably achieve better performance. This is really parallelizing one FFT. Okay. Anyway, so there is a problem. There are big differences. So,
one
yeah.
question. What
Okay.
are absolute running times? You mentioned milliseconds for the 1K, or?
What are the absolute running times? I don't want to say something that's off by a factor of 10 because it's very easy. So the runtimes are very short, and they have been improving over time. I remember when I got into this business, this size took 1 second, and then probably within 15 years it improved by a factor of 100 or something. But I don't want to say something wrong, so I don't want to throw out a number here. Okay, anyway, it's more about the principle. There's a big difference. So now, this is not specific to the Fourier transform. So here I have many applications from all kinds of different domains, some of which I mentioned at the beginning. And it turns out that for most of these computational problems, you have this effect, that the difference between a straightforward implementation and the best possible code, if it exists at all, can be quite large. And I know this because I've been teaching a class on this topic, and the students pick a project, and it has to be of mathematical nature, and it should not be too easy. And then what the students do is they learn techniques during the class. You hear the smiley people there know, right? So, you first create a straightforward implementation, then they try to optimize, and typically they get speed ups, I would say 5x, in that range. I've seen 1000x, sometimes only 3x, and everything is only single core. Parallelization is disallowed. So there's a problem. So straightforward code is typically highly suboptimal. Okay, so why is this? And now we come slowly getting into the connection to DSLs. So conceptually, what happens traditionally is in this picture here. So you have a computational problem, and you want to implement it fast on a given computing system. And there are in essence 2 parts. There's the manual part, and then there's the automated part. So there's the human. For the problem, the human has to pick an algorithm. Usually there are several choices, and implement the algorithm. Okay? And as we have seen, if you want to achieve high performance, the human has to also manipulate the algorithm, because as it is written, maybe it doesn't perform fast. After the implementation, you have a C program, and from here on, everything is automated. And now, the way I depict it is sort of the C program as kind of a singularity. And what do I mean by this? By that I mean that all the information that is up here is not available down here. Okay, and what that means is if you compile a C program for a Fourier transform, the compiler will not start compiling and then saying, oh, you compute a Fourier transform here, interesting, and man, you chose an iterative algorithm, that is really stupid. You have to choose a recursive algorithm with radix 8. Let's just swap it out, right? I mean, this is never going to happen. So there's an inherent limitations to what compilers can do. And that means an inherent limitation in this model to what you can automate. So compiler has no access to high-level information. Then algorithm restructuring is very difficult for a compiler, right? The analysis is not available because of the singularity. And then also there's a problem with choices, right? A human is very good in understanding. We have different choices, different algorithms, different way of doing things, and then to reason about it, okay? And all this is necessary to get high performance. Now, this is a problem, and in fact, a severe problem, because what this really implies is also that performance cannot be ported, right? You do all the tuning for one processor, and then comes a new processor generation, and you want to move the code, and the code is not optimal anymore, and you would like to just recompile, but that doesn't do the job. So a better picture would look like this, right? So kind of open the singularity and have more information available for automation, right? So that somehow such a system approach would be able to have to do a richer set of algorithm manipulation, algorithm selection, would have been able to do smarter optimizations, and also part of the implementation could be optimized. Okay, better picture. So to get there, and then maybe you could automate more or even everything down the road. So what do you need to do? Well, it's very clear from this picture. The challenge is to conquer this high abstraction level for automation, right? That's what traditionally humans are doing. Some of it should be done by this system, right? By this new approach. And it's very clear high abstraction level has to be automated, so you have to get it, you have to express this high abstraction level somehow. And it's pretty clear from this picture that DSLs are helpful in this scenario. Okay, because DSLs do exactly this, right? They enable you to express domain knowledge. Okay, and so we have implemented such a system, and this is also one of the lectures that you will learn a little bit about it. It's called Spiral, and it's a program generation system for a very small domain of transforms, and in particular fast Fourier transforms. Here's a website. And the idea was that the Fourier transform doesn't change over time, so let's build a system that generates Fourier transforms. And the goal was really to generate the best code possible, meaning at least beating all the others. And so what do you have to do? The Fourier transform is fixed, so the algorithms are known.
You want to beat FFTW?
Exactly, yeah.
How can you beat FFTW? By definition, it's fastest.
I don't think that's by definition is fastest. So you can look at papers. So we are doing
FFTW is perhaps misnamed.
If they say, yeah, exactly. Fastest for as Matteo and Stephen say themselves, it was a whimsical name chosen by some MIT students with a high level of confidence. So, okay, so what we did is to generate Fourier transform, we need to get the algorithm knowledge into the computer. And algorithms, here's a couple, expressed in a mathematical formalism that I'm not going to explain. You see that, but you see it's encoded as rules. These are all recursive algorithms. So you see DFT is broken down into other DFTs, and even some other auxiliary transforms may occur. Okay, and this is a mathematical representation. You can find it in some books. And we just said, okay, let's make this a DSL, right? I mean, the math actually provides a DSL. So put it into the computer, and then you can actually recursively combine them, and you get many different algorithms. Okay, and then Spiral works like this. The user specifies some transform. You expand the transform using these breakdown rules recursively. You get some expression in this DSL. Then we go from this DSL to another DSL, and then we go to actual code. So in this case, you see, for those who know, this is C code with vector intrinsics. Okay, so this is an automatic program generation approach. But now the key idea here is, and this is the relation between, one of the relations between DSL's performance, that these high abstraction levels are useful for performing optimizations that are not possible on the lower level. Okay, so for example, we showed that you can parallelize and vectorize efficiently by in essence restructuring the algorithm at this level, by applying rewriting, turning this expression into another one that has the right structure. And the same thing for locality at this level on this cryptic language. Okay? And this was really when sort of we came up with the approach in the early 2000s, that was really a surprise to many people, because typically you think that the higher you go in the abstraction, the less you can do for performance, right? Because performance is this close to the metal thing with registers and caches that in reality, particularly if you're in programming languages, typically you don't want to deal with that, okay? But it's necessary and compilers do it. So, but here the interesting thing is the high abstraction level can help with performance, okay? And that seems a contradiction, but if you think a little bit about it, it's not. Okay, and then we use search and learning approaches to handle choices. Okay, so you see the use of a DSL here is kind of a peculiar one, because the DSL is used internally in the system. It's actually not meant to be used by the user. There are only so many algorithms. We encoded them in the DSL, put them into the system, and then the system internally plays with these expressions, and you never get to see them. So this is an internal DSL. Not in the sense mentioned before. It's a non-user facing DSL. So the user is not meant to program in this, okay? Only the developers of the system. But you see that if this idea works, you could maybe generalize it. And that brings us to next effort, Delight, from the group of Kunle, who will only come on Wednesday, and together with Tjark and Martin, and takes this sort of a step further, or let's say in a different direction. So the idea was here, let's do something similar, but make it broader in use, but then maybe not go for the best possible performance just for very good performance. Okay, so different trade-off. More general, and maybe not the highest possible performance got good performance. And so what they did is, was briefly mentioned by Martin before, they developed a whole bunch of domain-specific languages for particular domains. So for example, machine learning, right? And these are user-facing, meaning a machine learning expert is meant to program in this language. Okay, and the language is designed to make this easy. In essence, you take your algorithm from the book, and then you can directly write it down. Okay, so it's broader than this FFT thing I showed before. And then, so this is, and the DSL here depends on the domain. And then they compile into an internal representation. And this internal representation, not exactly as it's shown here, is actually the same for all these programs. It's a normal programming language enhanced with primitives like reductions and things like that, that then can be mapped to different architectures. So the idea is then this internal DSL, which again is a bit at a higher level, is then mapped differently depending on the platform, right? Which could be a GPU, or could be a multi-core CPU, and so forth. Okay, so you see, similar idea, like two levels in this case, also of domain-specific language to enable different things. Just here you are user-facing, but you still have the ability to map well. Kevin, was that a reasonable explanation? Did I miss any important feature?
It's good.
Okay, it's good. So Kevin says it's good. So Kevin, Kunle comes only. You will also participate in the lecture on. Do you want maybe with the standing up thing? Or this is Kevin together with Kunle. They will do the lecture on Delight. Okay, and then here another effort, similar philosophy on generating fast database code, and just want to show the picture here. So the idea is, again, you want to have a system that is more general than spiral, in this case for database operations, queries and transformations, and you want to produce very fast C code. And you see again there's this multi-level approach, and for each level there's again a different DSL, so multi-layer DSLs. And again, the use of these multiple layers is to enable different optimizations at different abstraction levels. Okay, so it's interesting that sort of for every optimization that you can do, there's sort of the right abstraction level. Okay, and that's a theme that goes across these efforts, right? So for example, here's a representation as loops and multi-tables that enables, for example, structural transformation on tables and so forth. Okay, so same idea, but database domain. And the lecture will be given by Christoph Koch, and who's back there. So maybe just have a look. Christoph, did I do a reasonable job?
Good job.
Thank you. Okay, thank you very much. Okay, so And that concludes my presentations. So I'm happy to take questions. Thank you. Any questions on performance? Okay, good. Then I hand over to Boyan. Maybe you want to say no? No? Okay, then what is the next step? We are done and go for the break?
We are done and go to the break. So Christoph, you have no? Cool. So